So recently I was watching a YouTube video called How We Solved the Home Wind Turbine Problem, made by a YouTube channel called Undecided with Matt Ferrell. Now, this channel is known for being, shall we say, slightly too optimistic about certain new technological developments, and I think that is the case here as well, because I think the problem with home wind turbines definitely hasn't been solved, and I also don't think that's going to happen. Now, the problem with small wind turbines for home use has always been that they simply don't generate nearly enough electricity to be worth the investment. But according to Matt Ferrell's video, that is now about to change because, apparently there have been some developments in the world of small wind turbines, and he mentions a couple of startup companies that are working on new designs that are supposed to solve this problem. But I think that is not the case, and before I get into why I think that is, I'd like to make clear that I'm actually not against wind turbines. In fact, I like them a lot. I think they're fascinating pieces of engineering. In fact, I've built a small wind turbine which I put in the backyard, so we might talk about that one later on in this video as well. But I think that a lot of what is said in Matt's video is simply way too good to be true, and I'd like to explain to you why that is. So this is going to require the use of the whiteboard. So on here I've listed some things that might look a little bit hairy at first, but I promise it's really not going to be too bad, okay? So first of all, up here we've got this equation. Now this equation right here tells you exactly how much power you can produce using a wind generator or wind turbine. So it says that power is equal to 0.5 times the density of air times the area, so that's the size of your turbine, times the speed of the wind to the power of 3, so cubed, times the efficiency of your wind generator. Now this efficiency has a theoretical limit of 60%, or 0.6, due to something that we call Betz's law. We're not going to go into that in today's video, so if you want to know more about that, you can wait for some day that I make a video about that, or look it up on the internet. But essentially all it means, all you have to remember about it for now, is that it limits the efficiency of any wind turbine to a maximum of 60%. In practice, wind turbines will have efficiencies significantly lower than 60%. So let's just run a little example, to familiarize ourselves with this, right? So let's say that we have a 1 square meter wind turbine placed in a 10 meter per second wind, so it's quite strong wind. How much power could it generate? So we do 0.5 times 1.2, that's the density of air, times 1, the surface area, right, times 10 to the power of 3, that's our wind speed, times 0.4, so we're going to assume that it's a 40% efficient wind turbine. That's pretty impressive for a small turbine like this. That's going to give us a power number of 240 watts. So if you look at this, you might think, well, that's not too bad, right? 240 watts for a 1 square meter device. That's really good. That's probably better than what you could do with a similarly sized solar panel. And you can imagine that if you keep that running for an extended period of time, it can generate quite a large amount of electricity. But of course, in practice, you're not going to have that 10 meter per second wind all the time. The wind changes from day to day. In fact, the wind changes from second to second. So if you want to get an estimate for how much the wind turbine produces over the course of, let's say, a year, you're going to have to combine this equation with weather information or, measurements of the wind speed. So that's exactly what we are going to do next, right? So we're going to take our 1 square meter, 40% efficient turbine, and we're going to combine it with some weather information to work out how much energy it could produce. Now, I live in Holland, so I went to the website of the Dutch Weather Institute, and I downloaded a bunch of wind speed data. So what I did is I downloaded a big file that contains wind speed measurements of the entire year of 2023. So this file contains the wind speed measured for every single hour of the entire year of 2023, measured along the west coast of the country, which is a pretty windy area, by the way, so that should be good for a wind turbine. So now in theory we can take that data and combine it with this to work out the production of our 1 square meter example wind turbine. But there is a problem. And that problem is that this wind speed data is, these measurements have been taken in a wide open field 10 meters off the ground, which is, excellent for taking measurements of the wind speed. It's also excellent place for a wind turbine, but it's not the kind of situation we're interested in, right? Because we were talking about home wind turbines, residential wind turbines, and so in this case the turbine would be placed in a village or in a town or some kind of regular neighborhood with houses and trees and obstacles, right? And in that kind of environment, the wind speeds are going to be lower than in the environment where the measurement data came from. So we need to take that measurement data, we need to take those wind speeds and somehow convert them into different values that are more realistic for the situation that our example wind turbine is located in. And for this, we're going to use something called log wind profile. So the log wind profile is essentially a curve that looks like this, and it describes how the wind speed increases as you get higher up from the ground, which makes sense because the ground and all of the obstacles that are on it slow down the wind, and so the further away you get from the ground, the higher the wind speed becomes. Now, one very important parameter that goes into that formula, into this equation, into that log wind profile is called ZO, or the roughness length. And that parameter describes the roughness of the landscape. So for instance, a flat plain with grass on it has a roughness length of about 0.03, whereas a small village with a couple of houses and a couple of trees might have a roughness value of around 0.6. So what we can do is we can take this equation and rearrange it a little bit, which is what I've done here. Don't know if you can see that with the microphone. Rearrange it a little bit, and then what we can do is we can vary that roughness length and see how it affects our wind speed. So for instance, let's say that we've measured a wind speed of 10 meters per second in an open field at a height of 10 meters off the ground. So we fill in 10 right there, we fill in the height of 10 meters in both cases, but we change our roughness length from 0.03 to 0.6. So we're going from an open field to a situation that's more like this with a couple of obstacles. That would change our wind speed from 10 meters per second down to about, if I recall correctly, 4.8 meters per second, which is significantly lower than the 10 meters per second that we started with. So you can see we got a massive drop in wind speed by changing the landscape from that flat open field to a small village or a small town. And there are a couple of things to notice about this. First of all, we're still assuming that we're above all of the obstacles. So we're still not, this is not because we're behind a tree or behind a building or whatever. We're still above all the rooftops. We're still out in the open. This is purely from the friction that the buildings below us are creating. Secondly, this is already a big drop in wind speed, but wind speed is cubed in our power equation. It's to the power of 3. So imagine what this drop is going to do to the performance of any kind of wind turbine we might put here. Now, I should point out that this is of course a very rough estimate, right? We're using some super basic equations to compute something that is actually very, very complicated. But if anything, this simplified version is probably going to present optimistic numbers compared to the actual situation. So in reality, it is likely that the wind speed that you measured above a village would be even lower than this. So now what we're going to do is we're going to take the wind speed data from that file and we're going to run it through this to convert it into a new set of wind speeds that we're then going to use in combination with this to calculate the production of the wind turbine. So essentially the way you do that is you multiply, or you put the wind speed number for every single hour into this equation, so you get a power number for every hour, then you add all of those hours up over the entire year, and you get the total number of watt hours. You then divide it by 1,000, and you have the number of kilowatt hours that it generated. And if we do that, we get to a grand total for the 1 square meter turbine of about 69 kilowatt hours. Now, first of all, that is not intentional. I know what you're thinking. It is not the case, right? I didn't craft these numbers in a way that it gets to that number, although that would have been great, of course. But I wish I'd done it on purpose, but I didn't. Secondly, that is a very small, very disappointing number. I don't think I need a whiteboard to explain that 69 kilowatt hours is way too little energy for a, let's say, 1,000 or 1,500 euro kind of wind turbine, because that's sort of what it would cost if it's 1 square meter in size. And I'm being optimistic about the price there. That's just not going to pay for itself in a realistic amount of time, or at least not in an amount of time that it would actually keep working. And that's why this turbine simply wouldn't be worth it. And keep in mind that this was a very favourable example for the wind turbine, because we assume that it was 40% efficient, which is very impressive for a small turbine like that. We assumed that it reaches that efficiency at any wind speed. We also assume that it captures wind equally well from all directions, so it's perfectly omnidirectional. We assume that it's not being blocked by any obstacles, so it's above all the rooftops, all the trees, whatever. Essentially, we gave it an extremely good case, and yet it only made 69 kilowatt hours of energy. So in reality, the number is probably going to be even lower than that. Then I thought to myself, wouldn't it be cool to see what this turbine would have done if we did actually place it in a wide open field? So I ran the numbers again, but this time directly with the wind speed measurement data. And in that case, we get to a number of over 600 kilowatt hours, which is amazing, right? And if we, even if that's way too optimistic and you have to cut it in half, 300 kilowatt hours is still a very impressive amount of energy. And that's the sort of amount you need for that turbine to start paying for itself. So in that case, it would actually be worth it, very much so. And so that tells us something very important about wind turbines. And actually what it tells us is, well, something that a 9-year-old could have told you too, right? Which is that they work really well in places that have plenty of wind, and they don't work well in places that don't have a lot of wind. And that is really the reason that home wind turbines aren't a good idea. Some people also think that it's about the size of the wind turbine, but that's not really the case. I mean, there is an advantage to bigger wind turbines, right? They are a better investment as they get bigger. But that's not really the core of the problem here, because as I've demonstrated here, even that small 1 square meter turbine could be a really good investment if it was placed in that open field and it got enough wind. And, vice versa, the opposite is also true. If you took a big turbine and put it in a backyard or on top of someone's house, then you'd have a really big, really expensive turbine that is not going to pay for itself, because the environment with all of its obstacles slows down the wind so much that your turbine just doesn't produce enough energy. So when I look at videos like this that talk about, revolutionary new types of small wind turbines that are going to change everything, and this time it's finally going to be worth it, I know that it's not going to work. And that's because the wind turbines themselves aren't the problem here. The problem is the location you put them in. Even if you had some kind of magical turbine that uses wizardry to achieve impossibly high levels of efficiency, then there still wouldn't be enough wind energy in that area to begin with for it to make actual sense. So you might be wondering, what about the wind turbine that I have right in the backyard? Well, I built that wind turbine for fun, because I like making stuff and I've always wanted to own a wind turbine, so at some point I just decided to build one for myself. And it's actually a great project. If anyone is looking for inspiration for a DIY project, I would highly recommend it, because it's great, and it's fantastic to see something that you built from scratch actually generates power that you can then use to charge your laptop or even my e-bike sometimes. And that is really nice. And on a good windy day, when that thing gets up to full speed, it can generate up to about 150 watts, which is not too bad. But then if you look at its production over, let's say, an entire year, then the amount of energy that it actually outputs is a marginally small amount compared to the little solar panels that I also have. So I have like a couple of little solar panels, and those perform orders of magnitude more energy on a yearly basis than that wind turbine. And so, if you want a wind turbine because you think it's cool or because it's a DIY project, then absolutely go for it. But it's probably not going to be worth it from a production point of view. Now, finally, there is one more thing that I think I should address in this video, which is very high local wind speeds. So what I'm talking about is, you've probably had this at some point in your life where you're walking down a street in a city or in a town, and at some point you reach a spot where the buildings are arranged in a particular way and the wind comes from a specific direction that causes very powerful wind in that spot where you are, and you almost get blown away by it. And sometimes this also happens in natural environment where the mountains are arranged or other types of obstacles are arranged in a certain way, or the wind like rushes down a canyon or something like that. Basically situations where you wouldn't expect a lot of wind because there are lots of obstacles in the way, but the obstacles actually happen to be arranged in a particular way that pushes the wind through a certain opening, or somehow channels it to actually produce more wind in a very specific spot. Now, surely it could be a good idea to put wind turbines in spots like that. But if you look at the wind in an urban environment or an environment with lots of obstacles, on average it's going to be much lower. And so, on average, it's not going to be a good idea to put wind turbines in that environment, even if it is a good idea to put wind turbines in a couple of specific spots in that environment. Anyway, that was about all I wanted to say for now. I hope you've enjoyed this video. If you did, then maybe consider subscribing to this channel. And of course, all that's left for me to say is then thank you for watching.